Welcome back, everybody. Today I'm going to be completing part D of homework 4 for process dynamics controls. It's the last one, and what we're going to be doing today is we're going to explain how we can use cascade control to refine the control of the temperature of an exothermic reactor by controlling the makeup and flow rate of the cooling water going into the cooling jacket of such a reactor. Now, to get started here, I'm going to break down exactly what we're talking about here instead of just speaking it out. So, we're talking about an exothermic reactor. So, if I just generally draw a reactor, say we're talking about a CSTR, got a cooling jacket, we have got our agitator, and let's say that we've got a temperature probe up here for our reactor, which has got a TRSP, a reactor temperature set point, but we've also got the temperature here for our jacket, we're going to call TCW, which will have a corresponding set point TCSP. We also know that we're going to have our cooling water flow rate coming in here. We're going to have our QCW, which will also be coming out of here. We're going to have our inlet flow rate of our reactants, which we'll just call Q. This Q is going to have a couple factors to it. It's going to have the temperature of the reactants coming in. It's going to have the concentration C, and then it is also going to have, so we got our temperature, concentration, and then just, the flow rate itself, the Q of the reactants. We'll have that coming in as well. Let's see. Need anything else? I don't think so. And what the idea of this is going to be is we are going to look at our cooling water. Our set point, and use effectively a valve to vary the flow rate of our cooling water to adjust eventually the overall temperature of our reactor here. Alright, now we've got our overall diagram for our potential reactor here. We're going to go ahead and try to draw the block flow diagram. So we know coming into our reactor, we're going to have our overall reactor temperature set point, which is going to be our TRSP. So down here, which will go into a comparator, which will then go into our first controller block, which right here, we'll draw that out, which is going to be our G for our reactor temperature control. Which will go to another comparator, which is going to go to our G for our jacket temperature control, which is another GC. These are both going to be GCs, so control transfer functions. which is going to go into the process transfer function for our jacket, which we're just going to call our G. And then, of course, coming out of this process, we might want to consider if we have a disturbance. So we're going to call our GD here, coming into here, which will be controlled by the temperature of our cooling water. And remember that our jacket coming into there, we've got our QCW, flow rate of our cooling water, and then coming out, we have the temperature of our jacket. And then this is going to go ahead and come back around to here. And then coming out of here, coming out of our jacket control, we're going to be looking at our process transfer function for our actual reactor. So we're going to say our G reactor is up next here. And as we discussed over here, we've got several things coming in to our G reactor. First and foremost, we've got our GT, which is fed by the reactant's temperature. We've got our G concentration, guided by the concentration. We've got our Q for our reactants going into our GQ. That all comes out, all of these different vectors come out to give us our actual temperature of our reactor. And of course, coming out of here, we're going to have another whole loop all the way out to this comparator at the very front. As you can see here, we've got an inside loop and an outside loop, which gives this the name, the cascade control, as it's a cascade coming down from loop, out to loop, out to loop, out to loop. We're going from the inner loops out to the outer loops. And the reason this helps for a system like this is we have so many different variables coming in here. We got our jacket water, we got the jacket temperature, the cooling water flow rate coming into the jacket, the temperature of that water coming in, the temperature of the reactants coming in, the flow rate of reactants coming in, the concentration of reactants coming in. So generally, you can use this cascade control to help refine the control for a complex system like an exothermic reactor temperature control. So now that we've got this pretty complex flow or block diagram here, we're going to move on, erase a little bit of this, and simplify this down so that we can find an actual overall transfer function for this entire system. So let me go ahead and get all this erased, and we'll move on to that part. All right, so now we've got this overall block diagram for our exothermic reactor system. What we're going to do is we are going to simplify this down because we're not going to want to be writing a whole bunch of transfer functions in terms of GR, temp control, stuff like that. So we're going to simplify this down into easily readable variables, and then we're going to use those variables to create some more general transfer functions that we can overall move on to Python and do a little simulation with. So, getting started here, instead of saying TRSP, we're going to consider that we just have a YSP, Y set point, which, like up above, is going to be going into a comparator, going into, as we discussed before, this is a control transfer function, so we're going to call this GC2, which is again going into another comparator. Then we've got our GC1, our inner controller transfer function, which will be going into what we're going to call our GP1, our initial process transfer function, which will go into our disturbance comparator. And then, of course, we're going to have our GD yet again. Of course, has a disturbance coming into it. comparator. We've got our first loop here. And then this is going to go straight out into our GP2, our second process transfer function. And we're just going to kind of build all of this, all of the GT, G concentration, GQ comparators. We're going to build all of that into our GP2. And then coming out of here, of course, we're going to have our Y. And a couple other things we're going to want to define is right before this second process, we're going to call this right here our Z, coming out of our second loop. And then going into our first loop, we call this E. And of course, the last part of this simplified block diagram, we're going to take our final flow and put it into our first comparator here. So now that we've got this simplified block diagram here, we can start to write out some expressions. So we know that our Y must equal our GP2 times our Z, because that's the only things we have coming into here. And furthermore, we know that our Z must also equal our D times our GD plus our GC1 plus GP1, or not G, not plus, GC1 times GP1 times E all divided by 1 plus GC1 G. And we also know that our E must equal our GC2 times our YSP minus Y coming out. So if we substitute that into this overall function here, what we get is that our Z must equal our D times our GD plus our GC1, GP1 times GC2 all times our YSP minus our Y all divided by R1 plus our GC1 GP1. We got this function right here. If we sub this into our original expression here, what we get is that our Y has got to equal our D times our GD times our GC2. There's a GC2 here as well. All divided by R1 plus GC1 GP1 plus R E times GC1, GC2, GP1, GP2, all times R plus P minus Y divided by R1 P1. And if we rearrange this to solve for y, we end up getting is that our y times r 1 plus r g p1 g p2 g c1 g c2 divided by 1 plus g c1 g p1 must equal r g d times g c2 over 1 plus g c1 p1 times d plus r g p1 g p2 g c1 g c2 over 1 plus g c1 g p1 times r y s p. Then we can go ahead and call this value right here beta, and this value right here for alpha. We sub those into our expression. What we get is a simplified expression that y equals alpha over 1 plus beta times our d plus beta over 1 plus beta times our YSP. And that right there is our transfer function for this overall system that we can use to go ahead and move into Python and code this up. So let's go ahead and move on to that part.
All right, welcome back to the last part of homework 4, part D, and the last part of everything, I'm pretty sure, for separations. For this very last step, we're going to simulate the unit step disturbance, rejection, and set point servo control for the following cascade control system. And the things describing this control system is we're saying that the inner control loop process is dictated by our GP1 equal to 1.5 divided by 2s plus 1 with a proportional only control guided by KC1 equal to 1, a disturbance transfer function GD1 equal to 1 divided by 2.5 times S plus 1. That's going to be our disturbance coming into our system. An outer process transfer function equal to 1 over 20 times S plus 1. And an outer PI controller KC2 equal with a KC2 gain equal to 1 and a reset time of 1. So that's a whole lot of variables to define. So let's get started doing that. So we're going to say that we know that our GP1 is going to equal that 1.5 divided by our 2 times S plus 1. And then we also know that our GP2 is going to equal, where is it? Outer process is going to be R 1 divided by R 20 times S plus 1. That's our two GPs that we're going to need. Our GD, our disturbance transfer function, is going to equal R 1 divided by 2.5 times S plus 1. Fantastic. And then we know that our KC1 is going to equal 1. Our KC2 is going to equal also 1. And then our tau I, that is our reset time, is going to equal 1. That gives us enough to figure out our GC1, which is just going to equal our KC1 since that is proportional only control. And then our GC2 is going to equal our KC2 times R1 plus 1 over tau I times S. And that should be everything we're provided in the question statement. You look through just about everything. That all looks good. So I think we're good to go ahead and define our alpha that we figured out on the board here just a second ago. So we know from up on the board that our alpha is going to equal our GD times our GP2, all divided by R1 plus GP1 times GC1. And then our beta is a little more complex here. That's going to be our GP1 times, which I gotta put parentheses around this as well. It's going to be our GP1 times our GP2 times our GC1 times our GC2, all divided by R1 plus our GP1 times our GC1. I believe those are our alpha and beta functions there. Hit a shift enter. So now we can go ahead and simulate our disturbance here. So we can see our t and our y disturb. We're going to equal to simulate. And if we remember the first part of that function, we're going to have our alpha divided by R1 plus beta. And then our usual lambda t is going to be 1. And we're going to do 500 and dt. We're going to do 0.5 this time around. And then we can go ahead and plot out this disturbance function. So we're going to say fig equals make subplots. We're going to do fig dot add scatter. We're going to say our x is equal to our t as usual. Our y is going to equal our y disturbance. And then I'll give it a name, call it disturbance. Shift enter. And then as you can see here with our cascade control, we have a nice pretty convergence right around 0, which is what we want for our disturbance. So now we can go ahead and look at our y reactor or y set point if we were talking generally. So we can say that our t and ysp, or first I need to do fig equals make subplots one more time. And then we can do fig dot add scatter. Set our x equal to our t, our y equal ysp. Our name can equal reactor. And I apparently completely forgot to put our simulation in here. So once again, we're going to need to do our t and our ysp. I'm going to set that equal to simulate. This time we're going to do beta divided by 1 plus beta. Lambda is going to equal, or lambda t would be 1. And then we're going to do n equals 500 and dt equals 0.5. And I believe that is all correct. I hit shift enter. Beautiful. So as you can see here, we are converging right at our set point of 1. So this cascade control is working to get rid of the oscillations in both our disturbance and in our set point and come to a steady state fairly quickly. So as you can see that this cascade control would work fairly well for a temperature control system for an exothermic reactor. I believe that is the final video for the end of the final video for process dynamics and controls. I will see you in the last one for separations.